In M-ary ASK and M-ary PSK, the messages which are patterns of n binary digits and where n is equal to log to the base 2 of m, where m is the number of messages, are encoded either into amplitudes or phases of a sinusoidal carrier. Now, we will study M-ary quadrature amplitude modulation, popularly known as M-QAM or just QAM. It is a more general modulation that includes M-ary ASK and M-ary PSK as special cases. In QAM, the messages are encoded into both the amplitude and phase of the carrier. QAM constellations are two-dimensional and they involve two orthonormal basis signals. These orthonormal basis signals are as follows: phi it and phi qt. This is known as in-phase carrier and this is known as quadrature carrier. Both are defined over the symbol duration, that is Ts. Using this orthonormal basis signal, we generate the QAM message signal set as follows. The jth transmitted M-QAM signal is given by this expression. This is phi it and this is phi qt, where this aij and aqj are information bearing discrete amplitudes of the two quadrature carriers. This shows that there are two phase quadrature carriers involved and each of them is being modulated by a set of discrete amplitudes, and hence the name quadrature amplitude modulation. Also note that aij and aqj are precisely the coefficients Sj1 and Sj2 respectively in the usual representation of the signal Sj in terms of the orthonormal basis signals phi 1t and phi 2t. The alternate representation of Sj is as follows. Now, in this representation, Ej is the energy which is the sum of the squares of the in-phase amplitude and square of the quadrature amplitude, and the theta j is the angle which is tan inverse of aqj by aij. So, in this representation we see that our QAM signal is combination of amplitude and phase modulation. Now, we will assume that our message or signals are equiprobable. Our signal constellation is two-dimensional. So, the optimum receiver would be the minimum distance receiver. So, your received signal RT is equal to Sjt plus the additive white Gaussian noise with 0 mean and the power spectral density as italic n by 2. Now, the minimum distance receiver can be implemented as shown in this figure. This is the correlation receivers in the in-phase channel, and this is a correlation receiver in the quadrature phase channel. Right? And R1 and R2 are the projections of RT on phi 1t and phi qt respectively. and similarly SI1 and SI2 are the projections of the signal SIT on phi IT and phi QT respectively. So, we compute the Euclidean distance and choose the smallest of that. Depending on the number of possible symbols M and the set of amplitudes Aij and Aqj, a large variety of QAM constellations can be realized. And this figure out here shows two of the signal constellations for M equal to 16. This is a rectangular constellation, whereas here you find it is two circles. Obviously, for a given M, an important question is how to compare different M-QAM constellations in terms of error performance. Let us attempt to find an answer to this question. Observe that for signaling over an additive white Gaussian noise channel, the most likely error event is the one where the transmitted signal is confused with its nearest neighbors. Therefore, in order to roughly maintain the same error probability, the distance between the nearest neighbors in all the signal constellations should be kept the same. So, with this constraint, the more efficient signal constellation is the one that has smaller average transmitted energy. The most important configuration of signal point is rectangular. Known naturally as rectangular QAM, the signal points are placed on a rectangular grid spaced equally in amplitude by delta amount in each direction or dimension. Now, in terms of energy, rectangular QAM constellations are not the best M-QAM signal constellations, but the average transmitted energy required to achieve a given minimum distance is negligibly greater than the average energy required for the best M-QAM signal constellations. So, for this reason, rectangular M-QAM signals are those most frequently used in practice. The most practical rectangular QAM constellation is one which carries an equal number of bits on each axis, that is n is even. So, you will have 2, 4, 6, 8, and therefore, the number of messages, that is M, is a perfect square which would be 4, 16, 64, 256. The rectangular constellation is a square constellation. This figure shows rectangular QAM constellations for M equal to 4, M equal to 8, M equal to 16, M equal to 32 and M equal to 64. The signal components Aij and Aqj take values from the set of discrete values, and the minimum Euclidean distance is delta as in M-ary ASK. The major advantage of rectangular QAM is its simple modulation and demodulation. This is because each group of n bits can be divided into ni in phase bits and nq quadrature bits, where ni plus nq is equal to n. The in phase bits and quadrature bits then modulate the in-phase and quadrature carriers independently. So, this generates in-phase and quadrature ASK signals which are then added to form the QAM signal before being transmitted. Now, at the receiver, due to the orthogonality of the in-phase and quadrature signals, the two ASK signals can be independently detected to give the decisions on the in-phase and quadrature bits. Based on these discussions, the modulator and demodulator of a rectangular M-QAM is illustrated in this figure. You have input bits, goes through the demultiplexer, we get in-phase bits, quadrature bits, selection of Aij, the number of Aij would be equal to 2 raised to Ni, where Ni is the number of in-phase bits, and the number of discrete values for Aqj will be equal to 2 raised to Nq, where Nq is the number of quadrature bits. We get two ASK signal, in-phase ASK, quadrature ASK, and both are combined to produce the QAM signal SJT. And based on this, we get the receiver for the same as shown here. We have in-phase ASK channel and quadrature ASK channel, both are combined with the help of a multiplexer to give the final output. Now, any rectangular QAM signal constellation is equivalent to two ASK signals modulating the quadrature carriers. So, the in-phase carrier phi it carries Ni bits and has 2 raised to Ni signal points, while the quadrature carrier phi qt has Nq bits assigned to it and 2 raised to Nq signal points. So, for square constellation, each carrier will have root m, that is equal to 2 raised to n by 2 signal points. Since the signals in the phase quadrature components can be perfectly separated at the demodulator, the probability of error for QAM can be easily determined from the probability of error for ASK signals. So, let us do that. So, probability of symbol error for a square M-QAM would be given as probability of error is equal to 1 minus probability of correct decision. Probability of correct decision will happen if there are no errors in both the ASK channels, which means that probability of correct detection is equal to 1 minus probability of error in any one of the channel and then square of this expression. So, this is the probability of correct detection in one of the channel. So, both the channels should correctly detect, therefore squared. So, the probability of this is the probability of error of root M-ary ASK. We are assuming M to be square constellation, and this will have 1/2 the average energy in each quadrature signal of the equivalent QAM system. Now, let us quickly recollect the MSK signal error probability. We know that probability of error for the MSK case is given by this expression. We also know that the delta is related to the average signal energy by this expression. So, from this two expression we can get the probability of symbol error for MSK in terms of the average signal energy. Now, once we have this expression, we can calculate the probability for our ASK channel. Remember, in our case, this M now will be equal to root M, and the energy, the average energy is going to be the half. That's why it becomes 3, and this M out here is now root M. So from here we get the probability of error in the ASK channel in our model to be equal to this value. Okay. So ES average by root N is average signal to noise ratio per M-QAM signal. Now, using this and using this relationship, we can find the upper bound. So, to find the upper bound, what we will do is we will neglect for large M's, we can neglect this term. So, if we neglect this term, this will be approximately twice of Q, this value, and if we use that as an approximation, in this expression we will substitute that approximation. So, it becomes less than or equal to, and on expansion I neglect Q squared factor, I get this equal to 4 times Q. This is valid for n greater than or equal to 1. Now, in this EB by root n is the average SNR per bit. So, the plot of the symbol error for M-QAM is as shown in this figure here as a function of EB by root n for various values of M. The upper bounds plotted in this figure are based on this equation and can be seen to be very tight at high SNR. So, the exact and upper bound they merge for high SNR value. This is true for all M equal to 16, M equal to 64 and M equal to 256. Since both QAM and M-ary PSK are two-dimensional signal sets, it is of interest to compare the error performance for any given signal size M. Now, let us do that, and to do that let us recollect the probability of symbol error for M-ary PSK, which was given approximately by this expression, and the probability of symbol error for M-QAM has been just derived to be equal to this value. Now, remember here that average signal energy is equal to n times the average bit energy, and that is how we got this expression, and based on this expression this was plotted. Now, since the error probability is dominated by the argument of the Q function, one may simply compare the squared arguments of these Q functions for the two modulation formats, and the ratios of these two arguments is defined as Km. So, we will take the square of this and divide it by the square of this quantity. If we do that, we get this quantity, and we call this to be as Km. So, in this case, when M is equal to 4, Km turns out to be 1. So, what this shows that 4 PSK, that is QPSK, and 4 QAM are the same modulation format. Right? This is not very surprising. However, when M is larger than 4, it is seen that Km will be greater than 1, which means that M-QAM yields better performance than M-ary PSK. So, the table here illustrates the signal to noise ratio advantage of M-ary QAM over M-ary PSK for several values of M. For example, 64 QAM has about 10 decimal signal to noise ratio advantage over 64 PSK modulation. But it is important to remember that this advantage of course is gained at the expense of increased sensitivity to amplitude and phase degradation in the QAM transmission. Now, we have studied M-ary ASK, M-ary PSK and the hybrid of M-ary ASK and M-ary PSK in the form of M-ary QAM or simply QAM. Now, one more M-ary modulation scheme is left out, and that is M-ary FSK, M-ary phase shift scheme. We will see that this modulation scheme utilizes the signal constellation, which is very different from the modulation schemes studied so far, and this we will do next time. Thank you.